Okay, so today we want to start working with vectors. I'm sure you've heard the phrase before. For us, it's going to be a line segment, and it's going to have both a magnitude and a direction. Okay, typically we've worked with what are called scalars, which just have a magnitude. So the way I like to think of the difference is if a car is driving 50 miles per hour, it has a magnitude. If a car is driving 50 miles per hour east, it has a magnitude and a direction. Right? So, or if your physics, velocity is a vector, speed is a scalar. Right? Speed is just the magnitude. Velocity has both the magnitude and the direction, so it's a vector. So the way we're going to think of it is we're going to work with vectors in 2 dimensions on the coordinate plane. The math and the ideas all work the same if you go 3 or even more dimensions. You can do the math with vectors for things that you can't picture in your head because there's more than 3 dimensions, but the math all works the same. It just kind of, the same process, just more pieces. Okay, so it's a line segment with an assigned direction. A is the initial point and B is the terminal point. Now with that, it's interesting, it's important to note that the vector, we're going to talk about its components, but the same vector can start at 2 different places and it's still the same vector. So say that we have a vector that starts at 0, 0. That's kind of the standard position to start them for a lot of things. But say it goes 2 to the right and 3 up. Right, so we have the initial is at 0, 0, and then the length is important, and then the arrowhead is going to be at the terminal point. Okay. Now it would be the same vector if it started down here at, say, -1, -3, if it still went over to up 3. Right. We still have the same vector, it just had a different initial point and a different terminal point. It's still the same vector. So I always think of a vector as like it was a movement, right? If it's saying it's going this far right and this far up, that's how the vector is defined there. So the length of the segment is also called the magnitude. Okay, it's also a length, so we can also think of it as like an absolute value. That's the symbols that we'll use here soon. Any questions so far? We tend to do most of our mathematics with a vector in component form. So this is on your note sheet there, but basically what it says is the component form is we have if a vector v. Now another thing when we write vectors, in a textbook or on your note sheet, they'll always be in bold type. When you're writing in pencil or dry erase, bold is not really an option. Right? So what we do is we put a little arrow over it. Okay? So vector v, if it has an arrow over it, we know it's a vector. If it doesn't have an arrow over it, we know it's a scalar. It is important to include that when you're talking about vectors. So if a vector v in the plane has the initial point x sub 1, y sub 1, and terminal point x sub 2, y sub 2, these are just x, y coordinates, then its component form, then the component form of v, let's say that. The vector v, and we use these angled brackets here, and it's going to be the terminal x minus the initial x, and the terminal y minus the initial y. So that would give us our component form. And what we're going to find is the first component tells us how far we move side to side. The second component tells us how far we move up and down. So both of these vectors that we drew over here, we said they both go over 2 and then up 3. Right? So if this vector here was given a name, called maybe the vector u, it would have components 2, 3. Right? And we use these angled brackets so that we know it's not an ordered pair, but we know it's a vector. Again, it tells you about the movement. It doesn't necessarily tell you where it starts or where it ends. It tells you how it changes. So I kind of think of them as a change thing. I think is a helpful way to look at that. So some examples here, just kind of making sure we understand that definition of what the component form is and how the vectors kind of move from an initial point to a terminal point. Is for A here, we have the component form of the vector u. We want to find it with initial point -2, 5 and terminal point at 3, 7. So to do that, I mean, you could draw a picture, but so if you did make a picture, it would look like let's see, 1, 2, 3, 4, 5, 6, 7. So let's see, we have initial point at -2, 5. And then we have a terminal point at 3, 7. So again, remember our arrowhead is going to be at the terminal point, right? So it's not a line, right? It's not, you just don't extend it forever and then throw an arrow on the end. It actually, the length means something. That's the magnitude of the vector. So we could see that we went over, what, 1, 2, 3, 4, 5 units, and we went up 2 units. So I expect the component form to be 5, 2. Let's just kind of check the math here. Would be vector u has component form, the terminal x, which is 3, minus the initial x, and then the terminal y minus the initial y. And that's going to give us 5, 2, just as we expected, right? So that means the vector goes 5 to the right, goes 2 up. And it is important which is initial, which is terminal, because if you switched them, you'd get -5, -2, which would be the opposite vector, right? It would go left 5 and down 2, which we use sometimes. Like in subtracting vectors, you can think of opposite vectors sometimes too. All right, so here for part B, if the vector v has components 3, 7, is sketched with an initial point at 2, 4, what is the terminal point? Well, we could go back and write this whole formula out and kind of set things up, but really what this is saying is we start at 2, 3, so I'm sorry, yeah, 2, 4, and what are we going to do to the x value? We're going to add 3. So the terminal point would be 5, and then the vector has its second component is 7, so that means up 7. So if we start at 4 and then go up 7, that'll take us to 11. So the terminal point would be 5, 11. Now to check that, you know, if you think about the vector v, we know it should be 5 minus 2, and then 11 minus 4, which would be 3, 7. So it checks out that way. But that's all we're doing. It's just this idea of movement. It's a movement. All right, so the third one is sketch the vector w. And notice, I usually don't write a full arrowhead. You kind of get lazy. I do that simple. It's pretty common. Is the component, the vector has the components 2, 3. Like you wouldn't call them points, they're components. And we know it's a vector because of the arrow and because of the angled brackets with these initial points. So we could actually probably just sketch them all on the same grid. Fine. So from here, the one that starts at 0, 0, you might hear that called as like your standard position vector. Right? A lot of times we tend to use that one. Now this will only be as accurate as my spacing, which we'll see. So for the first one, we have an initial point at 0, 0. The vector is 2, 3 as its components. So we'll go 2 to the right and 3 up. So for that, that would be the first one there. Initial point at 0, 0. The terminal point would actually be at the point 2, 3, which is kind of an appealing part about standard position. If we start at 2, 2 is the initial point, we're still going to go over 2, up 3. And it's going to look like that. Hopefully they look parallel. Hopefully they look like they're the same distance. That they should. They should be the same length. It's the same magnitude. They should have the same direction. We'll talk about how to do angular direction next week. This was a 2. I just drew over it. If we start at -2, -1, we're still going over 2. We're still going up 3. So it's going to look like that. If we start at 1, 4, still going to go over 2, still going to go up 3. That's going to look like that. So they should all be facing the same direction. They should all be parallel, they should all have the same length, roughly. Any questions with that? Okay, so the next thing we want to talk about is the magnitude of a vector, and the magnitude is just the length. We just tend to use magnitude. To indicate that we're finding that, we use absolute value bars. That's just the distance, the length. So the magnitude or length of a vector v, I forgot the arrow, with components a, b, is just the square root of a squared plus b squared, which is just the Pythagorean theorem, correct? You're going over a, you're going up b, that's just the distance between them. So that's why it is the way it is. So we have a few examples here. We're given that vector u has components 2, -3, right? So to find its magnitude, the magnitude of u would be the square root of 2 squared plus -3 squared. And then from here, the magnitude of the vector u would be 4 plus 9 would be the square root of 13. Again, you're squaring, so there should not be any negatives in there because you're squaring, right? And we're going to have these are going to be real numbers. We're not going to have any imaginary units or anything. The next one we have here is vector v. Has components 5, 0. Guess what its length is? You don't have to really calculate this one, do you? It only goes one direction, correct? It only goes to the right. How far does it go? 5 units. So what do you think its magnitude is? 5 units, yeah. Now you could do the math if you wanted to, but it's still going to give you 5. It doesn't change. And then we have w, which is 3/5, 4/5. This is a special type of vector. Can anybody guess what's special about this one? It is a fraction, which is kind of makes it special in its own right. There's another special thing about it. Anybody? Let's check out its magnitude and see. So to find its magnitude, we get the square root of 3/5 squared plus 4/5 squared. Yeah. And then from here, that gives us 9/25 plus 16/25, which is just 1, correct? And the square root of 1 is just 1. So this is called a unit vector. That's something we talk about later on, a unit vector. So that would just be a vector with length 1. Or magnitude of 1. Pretty much if you hear unit in math, it tends to mean 1. Right? Unity or unit tends to mean 1. All right. Okay, so to finish up the note sheet here, we're going to talk about algebraic operations on vectors. One thing to kind of note that will really save you a lot of headache as we go through this whole unit, we tend to use u and v a lot as variables for vectors. When you take calc next year, u and v come up a bunch with some calculus rules. The sooner you can realize how to write your u's and v's to look different, you're going to be in good shape. Because if you get in a hurry, a v can look a lot like a u if you get lazy. So what I do is my U's always have a pretty big, I don't know what you call that, the stick thing that keeps it like from falling over. You know, the leg or the stem. They call that the stem. But it always has a nice big stem on it. Even if my V's get kind of sloppy and kind of in the middle ground there, I know that's still a V because it doesn't have the little stick holding it up. So just find a way for you to be able to write the letters so you can identify them. That's like my T's will have feet on them so they don't look like plus signs. Just learn these little tricks. So algebraic operations, these are really, again, these are the way, if you were getting to pick out the rules, you'd probably pick to have them this way. So for this one, the first is if vector u has components a sub 1, b sub 1. We're intentionally not using x and y there because these are just the components, right? Even though a tells us how far to go to the side, b tells us up, this is not a point, it's a vector. And the vector v has components a sub 2 and b sub 2. Then, if we go ahead and add these two vectors together, u plus v, you take their first components, add them up, you take their second components, add them up, and that gives you your new vector. Okay. You could write it as that. Sometimes you'll even see it written as the new vector as u plus v with one arrow over it. That's not uncommon to see that also. Right? It's a new vector. Its name is u plus v. Let's see that. To subtract them, again, you take the component of u, subtract the first component of v, second component of u, subtract the second component of v, just as you would hope. In this case is c times the vector u. C is a scalar. Right? We could tell that, I probably could write it up there, but there's no arrow over it, so we know it's a scalar, so it's just a number. So this is basically, if you take 3 times a vector, it gets 3 times as long. Right? If you take -1 times a vector, it changes to the opposite direction. Right? So what we do is you multiply each of the components by c. Is how we're going to do that. So it's going to, does that make sense? It'll have the same direction unless c is negative, then it'll have the opposite direction. So just some work some things out here. I guess for this example, I needed to give us some initial facts here. So vector u is 2, -3, and then vector v is -1, 2. All right, so for the first one here, if we're going to do u plus v, we just add the components. So we're going to get 2 plus -1, -3 plus 2, and that's going to give us 1, -1. Is that good? There? To subtract them, we're going to subtract the components. So we're going to get 2 minus -1, -3 minus 2. And that's going to give us 3, -5. Everyone doing okay so far with this? Next up, 2 times the vector. So 2 times the vector, 2 -3 will give us the vector 4, -6. Again, I just took each component, multiplied by 2. I know it feels like distributing. It's really not distributing. It's really vector multiplication by a scalar, just a property. -3v. So this will make it 3 times as long, but since it's negative, it's going to make it the opposite direction. This v. So for this one, -3 times -1, 2. That'll give us 3, -6. And then lastly here we have kind of have a bunch of things going on. So 2 times 2 -3 plus 3 times -1, 2. And this is 4, -6, -3, 6. Again, just multiply the scalar in there. And just like we do with order of operations right here, we're going to multiply the scalar before we add them together. I think that makes sense to everybody, I hope. We add them together, and we get 1, 0. Just here to kind of show what's going on when we do this, I'll show an addition example for this first one here. On Monday, we'll do a little bit of graphing. You can put them end to end and stuff. But say that we want to have, let's look at just a sample plane here. Suppose we want to do vector u plus vector v. We want to show that graphically. Now, you can start vector u at any point you want, but it's usually easier to start it in standard position. So for the vector u, we know is 2, -3, so I'm going to start at 0, 0. I'm going to go 2 to the right and 3 down. So that gives us, that is the vector. That is the vector u. Now, in order to add these, what we'll do is you'll take the vector you're adding and you'll put its initial point on the terminal point of the previous vector. So for this vector v, we're going to move -1, 2 from this terminal point. Okay, so -1 would be 1 to the left, 2 would be up 2 units. That would be the vector v. And then the answer, the solution, would be the vector that goes from the initial point to the final terminal point. So if we look at this purple vector here, that would be the vector u plus v, or you could write it as u plus v with a single vector over it. And if you look at this, its components would be -1, 1, -1, wouldn't it? Which is what we saw right there. So it's a lot easier to actually add them together, like, when you're doing that. But other things you could do, like here, the negative tells you to switch the direction, right? Make the initial the final and the final. Well, I can show you that. So for that one, so let's see, for that one, -3v, right? We know that v is -1, 2, correct? So -1, 2. So v in standard position would look like that. Now, if you make it the opposite vector, it's going to have the opposite components, right? So if we think about the opposite of vector v would be 1, -2. So it'll be like that. So that's -v. Okay. And then what we'll do is to do 3 times that vector is I'm just using my little ruler here. There. So there's another one. And there's another one. So we can see that vector v in standard position, so this whole one is -3v. So this was 1, -2 to be the first one, and then when we did this, we ended up out here at 3, -6. Because we were in standard position there. So this has a movement of 3 to the right and 6 down. And again, I'm not terribly to scale, but you get the idea of how we could do things graphically as